Wow, yesterday was. I mean, I bought pizza for dinner like a whole weekend. I mean, eating is so bad this year. Yeah. What is this? What's this? So, it's on. Everybody inside. Right. No, it's happening. Now, Jacob. Yeah.
Hello, everyone. Please take your seats. So we are ready to start the next session. The first speaker is Jacob Muller, who will talk about black hole cinema.
Does that work? Perfect. Fighting with the microphone. Okay. Okay. Yeah. So, hello everyone. I'm not Frick. He cannot be here today, so I was asked to jump in. So I will be presenting the NGHT analysis challenge, and also this will be a black hole cinema. So there will be movies. So really, a lot of people worked on this, and it was really a great thing. So what is the NGHT analysis challenge? So the idea is to have some data where a lot of people can throw a lot of methods on there. And of course, the data should be as realistic as possible, but also have data sets which might not have the entire complexity to try out new things and then continue to grow with and adapt for new challenges. So the idea is to start with a realistic ground truth source model. So that can either be tailored to a specific science case or can have multi-frequency components. It can be static or variable. It might have polarization and things like that. And then once we have this source, this synthetic source, you also want to measure it as realistically as possible. So you want to include all the things that can and will go wrong in real observations. So, and you can also use different configurations of the arrays and yeah, weather, noise, and all of those things that can go wrong. And then there is this data set, or there are several data sets people can work on. And the nice thing is that then you have a common problem and you can compare the different methods and different scenarios. And depending on the method, this can either be images or movies. You can also fit parametric models and many, many more. So the idea is to go from the source through some simulated array to the data, and from the data, again, it's a challenge to reconstruct the image or the movie. So what is the motivation? So it is to explore the capabilities of these kinds of arrays for science cases, identify the strengths and weaknesses of the different algorithms and array architecture so that you can see on how changes in certain things affect the actual outcome of the reconstructions. It helps for the development of the algorithms because you're challenged with a real problem, more or less, or as real as possible. So you can see on how you perform and what you have to improve. And of course, it's very important to get input from as many people as possible because the challenges we are facing with these kinds of reconstructions are huge. So the more people contribute, the better it is in order to actually solve these kinds of reconstruction problems. Once again, so how does the data generation work? So there are several pipelines so first of all, you have these simulated sources, and then you have to consider all the different kinds of problems you get with the actual observation. And for the data generation, there were two different codes used. One of them was the data generation from EHT imaging, and the other one, the SIMBA pipeline, which really tries to include any step of corruptions on the way. So this includes weather effects, this includes antenna diameters, this includes pointing errors, and so on. So this really tries to measure this, include this entire setup for a realistic data generation. So which array was used? So one data set was always EHT 2020 configuration, and as a NGEHT, there was the reference array 1 used, which has nice UV coverage, 6 meter dishes, 8 gigahertz bandwidth, and median April weather was assumed. So this was the input of the data generation. And now a few words about the sources. So for the first challenge, the challenge was to reconstruct static images of these kind of sources using only thermal noise. And for M87, the Kappa chat model was used, and for Sagittarius A star, there was this RIAF model. And for M87, the goal is to reconstruct the extended chat structure, and for Sagittarius A star, the goal was to recover the shadows. So this was the focus of this challenge. And now here a few results for M87. So you have a lot of different algorithms. So you have EHT imaging, you have Smiley. There might even be clean, I'm not entirely sure. But you see on how these algorithms perform on the dataset. So on the left side, you see the EHT 2022 configuration, and then the improvement with NGEHT. And in fact, all these different kinds of methods are able to recover the extended structure of the chats given this setup. So this is really nice. So, and you can really compare and also see the improvements of the different methods of the strengths and the weaknesses. The same thing for the Sagittarius A star problem. There are also, again, many different kinds of methods, and they were also able to recover the shadow. But keep in mind, this is a static source. So there was not the complication with the variability, but nevertheless, many methods lead to qualitatively similar or very similar results. And you can see the improvements with the improved coverage. So now the other thing is you have all of these reconstructions, but you need some way to quantify on how good they actually are. And for that, Frick developed a lot of different metrics in order to check for certain properties of the images. One of them is this dynamic range metric, which looks at how large the dynamic range is. And you can use that to compute the dynamic range of an image in a certain way. And then you can compare the different methods and also the different configurations and then see how good these kinds of methods perform. So this was challenge 1. Now for challenge 2, it got a bit more complicated because now this Simba pipeline was used, which includes all the different weather effects and calibration problematics. And here now the input source is actually a movie. In this case for M87, it was GRMHD simulation by Razi Imami and Kaushik Chatterjee using this configuration. And basically it was 20 frames throughout a 5 months observation period. So roughly 1 observation per week of M87 using the different arrays. And also for 3 different frequencies, so 86, 230, and 345 gigahertz. So this is now one example of so what I contributed to this challenge and my colleague Philip Arras. So we reconstructed a movie of the setup for the different frequencies, and we were able to capture the dynamics of the evolution of the things going around the black hole. And of course, we can do this at the different frequencies. And if you get better data, then the movies will get better. But we can definitely reconstruct movies, and they look quite nice. So this was only one source for the challenge. Now, this is another simulated source. It's a RIAF model with a shearing hotspot by Paul Tiede. And there you have this one spot that shears into the black hole. So this is meant to model Sagittarius A star. And it has frames every 30 seconds. and it's a 4-hour movie. And using Sagittarius S-star setup, the goal was to also recover this kind of model. And there was also scattering involved. So for the different frequencies, you get different amount of scattering, which also has to be taken care of during the imaging. So one example for reconstruction using the StarReps algorithm, this is a reconstruction by Antonio Fuentes. You can see that you can recover the dynamics, and with NTHT, you really also get the substructures on how it actually shears in. So that's really nice. So for this method, there was a regularization regarding the change between the frames in order to get this continuous motion. So also NTHT will probably be able to resolve these kinds of structures. So finally, the last source or problem for this second challenge was a reconstruction of a GRMHT simulated source of MAT of Sagittarius A-star. So this time it is a 12-hour movie with 220-second time resolution. And yeah, it's this kind of simulation. Also, scattering was involved in all the different weather effects. And here we have a dynamic imaging reconstruction from Michael Johnson, using also regularization in the temporal direction. And you can clearly see that NTHT is probably able to recover all the structures, things that are going on around the black hole, and really to resolve the dynamics. Okay, so these were a few examples of the submissions. There were a lot more, but if you're interested in imaging or just want to play around, challenge 1, which assumes static sources, and challenge 2, which has these dynamic sources and weather effects and things like that, are still available. So it's a nice place to get started, to play around with. Yeah, there will be a paper upcoming summarizing the current results, and also containing a lot of these metrics to evaluate the performance, and then you can really compare on how the different methods perform. Yeah, there's the link if you want to start right now, and also there will be, or it's already a third challenge which recently started, which also includes polarization data. And there, the goal more or less would be to reconstruct, so either the polarization or a polarization movie, or probably the best thing you can do is a polarization movie in multi-frequency. So yeah, so if you're interested, you can just get started. Yeah, I think that's it from my side. I'm happy to take questions.
Thank you, Jacob.
Thank you so much for a good presentation. I have a little minor question about the image reconstruction between 2022 and the NGHT. So what is the main promising point if we consider the improvement from 2022 to NGHT? So both cases, the results shows us we can extract the clear jet feature for 2022 and NGHT, and what is the main perspective for NGHT?
Yeah, I mean, what we are doing here is imaging. So our result is an image. So we can look at different metrics of this imaging. But of course, if you really want to get down to the science results of these reconstructions, you need to put something behind that. So currently, this is not there, but you could easily do that. So if you're interested in how these different reconstructions affect the output of your further analysis, you could just do that. So the reconstruction should be available. And to answer that question, you probably have to do something like that.
Thank you.
Any other questions?
I've got one. This is almost certainly hugely off topic, but your simulation package doesn't really accommodate phase referencing type approaches. Is there any control of scheduling, or is it purely pointed towards self-calibration?
So that's for the simulation of the observation.
Simulation of switching between sources to see if you can get a lower frequency than.
Yeah, I must admit I'm not an expert on this Simba package, so I'm not entirely sure on what's in there and what's not in there. So you probably have to ask Freek. He can probably tell you more about that.
Sure.
Okay, if there are no further questions, let's thank Jakob again. The next talk is by Daniel Palumbo on site selection.
All right, can you hear me okay? Awesome. This clicker will hopefully advance. All right, wonderful. Hi, everyone. My name is Daniel Palumbo. I will be talking about how the site selection team has been going about thinking about where to put new sites. This is not the only concern that goes into the placement of new sites, but here we're going to be talking primarily about algorithmic optimization of science parameters for our array. Now, this is a talk on behalf of many people, especially Dom Pesci, who has done a tremendous amount of work here. And so I want to highlight all of their efforts and recommend that you reach out to individual people if you have specific questions after this talk. So this effort was kicked off a few years ago. In the beginnings of this culminated in a paper by Alex Raymond, which analyzed sub-millimeter weather optimization, or really it's a weather study, across the globe for a large number of potential NGEHD sites. And since then, we've only made our lives harder by thinking about more and more details of what makes a good NGEHD site. And this problem is not just complicated for reasons of individual details at sites. The problem is innately difficult and computationally complex. The value of a given set of new sites is, as we have hopefully become familiar over working with VLBI, innately quadratic in the number of existing sites, because each new site adds n squared new baselines, but also depends on how you are adding sites. If you add multiple sites at a time, you also need to worry about the baselines between these new sites and what they add to your array, and whether these are redundant with things you already have or not. And so any serious search, regardless of your technique, is going to end up being very expensive. So there's three approaches that we've taken so far, and I'm going to outline them. And these are not necessarily the only approaches you might employ, but they're what we've been doing so far. The first two are what I would call combinatorial metric evaluation, where you choose to add k sites at a time, where if k is 1, you're just adding one site at a time to a given base array. This is a greedy approach. Whereas if you are adding multiple sites at a time, in our case, we've chosen k of 5, this would be a brute force approach, where you're adding large combinations at a time, and you're considering all of the baselines between those sites in addition to baselines they form with your base sites. So it's necessarily more representative of what the future NGHD will look like than a greedy approach. And lastly, I want to highlight some excellent work being done by Hosun and collaborators, and also being run by Razi Amami on simultaneous array optimization and source reconstruction using a method called cosense. And I'll detail a bit of each of these. A general property of these is that because we are considering so many sites, initially we were considering something like 50 or 60 sites, it is much more useful at this stage to eliminate options than it is to find the optimal next generation EHD set of sites. Because the more we eliminate, the less expensive this optimization problem becomes, and we can start to change our metrics and do things that are more computationally complex. and make more serious decisions among potential sites. So the combinatorial metric search is essentially, we start with a list of potential sites and a list of base arrays that we want to consider, and we want to choose a number k of these new sites to consider at a single time. And we iterate through all possible combinations of k sites, in addition to combinations of base array configurations, dish sizes, bandwidth, frequency, time of year, source model, and really any other parameter that you think might modify the properties of your array and the properties of your synthetic observations. And so we generate synthetic data corresponding to all of these parameters, and then we compute a set of desired metrics. Now, why are we using these metrics when we could be doing imaging or model fitting? Again, it's computational expense. At this stage where we're considering so many combinations, we cannot afford to run full posterior sampling in Themis or whatever for every single one of these millions of combinations. So at this stage, we evaluate these fast metrics, which I'll get into. And then we want to find the sets of these hypothetical arrays which perform best by these metrics. So I'll outline these. The first of these is the filling fraction metric, which we consider as a proxy for imaging. This was first introduced by a paper of mine on space sites, but since then people run with it and use it on everything. Thank you, Dom, for this diagram, where all we do here is we take existing coverage, which has been gridded, and we convolve the coverage with a disk of size roughly 1 over a hypothetical imaging field of view, where this is motivated by half-widths of Bessel functions, and I can get into the details there. But the point is, the density, or rather the filling fraction of your coverage, where you're in a bounding disk given by your resolution, is inversely proportional to your hypothetical imaging field of view squared, roughly. And so this tells you how much of the information that you need you actually have. How much are you sampling with a given set of coverage? There's point source sensitivity, which is in the unresolved limit where you're just essentially integrating over all of your sensitivity in your array, just what's the dimmest thing you can find with all of your baselines. There's also angular resolution, where we just compute the natural weighted second moment of our coverage to get a sense of what our resolution element looks like and its size. And lastly, we have a cost model, which Aaron talked about yesterday. And I'm not an expert on this implementation, but it's a way of folding into our optimization the cost of putting sites in particular places with particular dish sizes. And so all of these require a source and a weather and a hardware model in order to be able to be seriously evaluated, because all of these have some sensitivity to SNR. So we generate synthetic data from a number of sources. These are just 2 examples. So given a source model and an atmospheric capacity at each site, which we take from 10 years of history of global weather instantiation, so we're getting all of the correlations between site weather. It's all naturally folded in. We generate data with some sense of the ad hoc phasing performance. So whether or not we have a really big sites in the array like ALMA will dramatically alter our ability to ad hoc phase, and this will be folded into the SNR calculations. And so then we can compute our synthetic data and then compute our metrics in a way that is somewhat representative of what our observations would actually be like on a given day in the last 10 years. And we run 1,000 Monte Carlo steps of this optimization, or excuse me, of this synthetic data generation to get some sense of the typical performance of a given set of new sites. So just as an example, this is the greedy method maximizing the filling fraction. So this is 1 site at a time in the compact imaging science case. So this is 150 microarc second field of view. And what we see when we use the EHD 2022 as a base is that once we get past roughly 5 new sites, we're starting to saturate the compact imaging filling fraction. And so what that means is that the NG-EHD phase 1 is already going to be transformative for compact imaging of MED7. Now, jet imaging of MED7, which we want to do, where we're making these connections at the 500 microarc second scale, like I said, the filling fraction scales like 1 over the field of view squared. So we are going to see immense improvement in jet images out to phase 2, but phase 1 is already transformative. The brute force metric comparison lets you generate somewhat complicated plots like this, where we can look at the best arrays by each metric and then score each site by how frequently it appears in the top 1% of all arrays, and where we're marking the top 10 here. And essentially what this does is, especially for the metrics which we find are most useful and most discriminating, like filling fraction and point source sensitivity for different science cases, we get a sense of which sites we should be targeting. In this case, this is a phase 2 optimization where we've baked in our phase 1 choices. I just want to highlight CoSense. So CoSense is still very much under development for its usage in site optimization. But the approach here is you have an Ising model that is building essentially a model of the value of pairs of sites. So it's a very natural application of an Ising model in their usefulness to the array, where given a source model, you are solving simultaneously for the optimal set of sites for producing data on that source model, and also the optimal reconstruction method via an autoencoder. And so in this way, we get a sense not just of how best to reconstruct an image given a particular set of data, but also which sites were most useful in generating that reconstruction. So this is a very clever usage of the Ising model. And really, it's perfect for answering the question of which sites were most necessary by using things like sparsity regulars, or really sparsity hyperparameters in training this model. And so the kind of information you get out of this are, in this case, this is for, I believe this is a Sajik star optimization. And so that should be SPT on the far right, where, of course, negative individual node weights are saying, or yeah, this is MD7, so the South Pole is not helping you, so it should have a negative value. And pairwise parameters, so this theta JK, are telling you which sites are redundant. So co-located sites are going to have a negative parameter value here, because of course, by this metric, they're not helping you too much, because the total flux is not super important in this particular optimization. And so you can start to add in more sites, and we can start to ideally eliminate more sites if we were to do, say, 50 sites at a time, by finding large swaths of our parameter space where potential sites are largely redundant. So I've included this slide mostly as a reference. Many of you are working on analysis of the synthetic data sets that we've generated. So this is here to tell you how our naming scheme works and what sites are where. So the EHD is this particular set of base sites. And when we say there's a partial EHD array, we've baked this down to 5, which we expect to be more regularly available. And the minimal EHD array, in our case, is just the LMT. And when we say that there's an NGHD phase 1, we're adding, for now, Baha, CNI, Haystack, LAS, and Overo. And phase 2, well, again, still being optimized, but in some of the test data sites we've released, you can see these 5. And so the equation for our naming scheme and our data sets is given below, where when we say NGHD or partial NGHD or minimal, you're just taking the partial or minimal EHD and adding the relevant sites from these phases. So when in doubt, just email us, but hopefully this is clear and we'll tell you what to, or how to treat your data. And so looking ahead, as these science cases and tools mature, we can get a better sense of what we're actually going to see with NGHD data. And if you ask anyone who has actually worked with this data, it is a very different character to current EHD coverage. There's much more of it. Their coverage is much more exhaustive. And it's generally much more expensive to run our model because there is just so much data. It's a very different beast. And so this is really the time to get involved because we are getting down into the sort of final stages. We're not fitting or trying to optimize a potential 60 sites. We're optimizing from among 20. So please go get your hands dirty, try these test data sets, get involved in these challenges. Sadly, the analysis challenge hackathon yesterday was not possible because Flake is recovering, but just going forward, let us know, are these optimized sites giving you what you need to do the most rewarding science you can? And if not, this is something we need to know now. But so far, it looks like the optimization is working. We're seeing really exciting test results. So I'll stop there. Thank you.
Thank you, Daniel.
Thank you for the nice talk. I was wondering, when you consider filling fraction, have you also considered a filling fraction of high sensitive baselines? For example, NGHT use stations with ALMA, for example, those high sensitivity baseline filling fraction must be important, I guess.
I see. So yeah, we've tried a modification of the filling fraction that's essentially weighted by the SNR, just to see, is this somehow more predictive of image success? It seems to be roughly equally predictive, but we have played with this. This is also slightly similar to taking a minimal EHT that's just the LNT and seeing, what are your most sensitive baselines sampling there. And so this is baked in some of the optimization tests we've done. It doesn't seem to matter much. As long as you can phase, most SNRs created equal. But obviously there are counterexamples to that if you're doing real science. But sure.
Thank you so much. So I would like to ask two questions. So first question is the design consistency or difference between static imaging process and the dynamic imaging process. So I think this result is based on the static imaging process, but is there any difference or consistency if we consider a dynamic imaging process?
Yeah, so one of the parameters that we search over is observation duration. Now, in the particular search slice I showed you, I believe that was a full night sample, although Dom should correct me if needed. Thank you. But we can also search over, say, snapshot coverage or 1 hour of coverage. And so when we get down into what I would consider the end stage, where we're choosing among a small number of very high probability additions to the array, that's when we want to be as exhaustive as possible and check the snapshot imaging case, the dynamic imaging case, where maybe integrating over a night or averaging over a night of all these metrics. And we have the tools to do that, but at this stage, we're still being a little exploratory.
And the second question is a little beginner, but how to design the scan time schedule process? I saw the few examples of the time schedule of each scan, but how to design?
So I think a particular duty cycle is assumed at 50%. Is that right, Dom? So we're not getting too fancy with it. I think it's presumed to be continuous 50% duty cycle as limited by ad hoc phasing over the duration of the observation.
Thank you so much.
So I have a more provocative question, Daniel. And that is, well, all these sites are great and you have put together a very nice optimization kind of exercise. But is there a merit to considering what our Korean colleagues talked about earlier this week, where they chose sites not necessarily for the best coverage, best site value, like being high altitude and all that, but also for ease of use, ease of integration into the array. For example, infrastructure, logistics of getting there, bandwidth of access, and things like that.
Yeah, so sort of two answers to that. One is, especially in phase one, a lot of our choices are not just governed by a success by our metrics, but also do we have collaborators there who are ready to work with us now? Is it sort of gut, in terms of our immediate knowledge right now, do we know we have sort of cornerstones in the ground there to actually build? Phase two, where we're looking towards potentially placing our own new sites in a slightly longer term, there's a little more room to be imaginative. That said, we are making an attempt to bake this into the cost model, some notion of accessibility and infrastructure. So we're trying to be sensitive to this in the sort of soft sense and also in the algorithmic sense, but this is ongoing work. Did you have a question, Jeff?
So you talked about the filling factor saturating a bit after 5 stations.
In the compact imaging case. Yeah.
In the compact imaging case. There's one reason, of course, to keep going well beyond 5, which is also weather contingency. So I know that you've added weather into all of these simulations that you're doing, but occasionally the weather will be so bad that you're just off the air and the snow will just clobber you. And we'd like to be in a regime where anytime we go out, there's sufficiently critical number of stations so that we can do the science we want to do, so that we're never in a case where we're just torpedoed for a night. That'll be very important for MAD7 movies.
Yeah, and if I could add to that, that was assuming the full EHT 2022 as a base array. If we're going to be observing every 3 nights for 90 days, that is not a safe assumption. And you will see that filling factor drop by a factor of 2 when you lose half the EHT sites. And so if you were to run that optimization with the minimal EHT, you would get a very different answer. So I would say the compact movie making case is benefiting a great deal from phase 2. Right.
Okay, Jono, did you have a question? Or? No, okay. I think we should move on. So the next talk is by Mark Kettinis on NGHT data management. Thanks, Daniel.
Does this work? You have it a little closer. Yeah. Okay. Maybe not. Okay. Thank you for giving the opportunity for me to speak about the data management technical working group that I'm co-chairing together with Lindy Blackburn, who unfortunately can't be here. So a quick overview. There's quite a significant data challenge in the NGHT. The idea is to quadruple the bandwidth compared to the current EHT, double the number of antennas, and to increase the observing time with an order of magnitude, which means that we'll have to deal with hundreds of petabytes instead of petabytes per. The data management working group is basically concerning covering a broad range of topics from getting the data from the instrument all the way towards delivering calibrated visibilities and maybe even beyond, because there is also data management challenges in sharing the data between teams, including possibly sharing simulations, the output of simulations. It would probably be a good idea to think of that in an integral way such that people can get the simulations and the actual data from the same location using the same infrastructure. We've constructed a team that's covers the globe widely, covers quite a broad spectrum of knowledge about correlators, high performance computing, data transport. But the team was formed fairly late in the process. More or less, it was complete at the start of the year. We had our first meeting in February. So therefore, we didn't make as much progress yet as probably would be good for the project. The plan that we have is to initially write a set of memos about the topics listed here. We started on the first three, which are in very draft status. Hope to start with the second set soon this summer, because this information will hopefully be very useful for the engineering team as input for the design, the conceptual design of the instrument. We've basically, for each memo, put down a set of questions as a starting for the team to think about and see if we can answer them. But the memos will also cover an inventory of what's currently available and what technology development is happening in that area and what we expect to become ready on the timescale of building NGHT. So the first one is on high performance computing and big data, where we would like to explore what computing facilities are already available for us to use, to run simulations on, maybe even do correlation on. What are similar projects with a similar data challenge do in that area? For example, we're fortunate to have Rosie Bolton from the SKA on our team, and the SKA, which is started building their telescope now, is a little bit ahead of us, so we can want to see what we can learn from them. Second memo is on data transport and related technologies. Obviously, we need to get the data from the telescopes to the correlator. We want to see how well the current EHD approach would scale, but also what new technology becomes available. An important thing is, of course, correlation. We have a correlator for EHD. In principle, should work for NGHD as well. It's a software correlator that scales quite well. But maybe the amount of data is so much more that we need to improve on that. And there are several options for that. We also start with a memo on the future of radio interferometry software, in the sense that we want to look at what our other radio interferometry projects doing. There's SKA and Meerkat have similar challenge in compute and in the amount of data, and see if there's infrastructure that we can share, and maybe even if there's algorithms that can be shared, and if there's any benefits in maybe co-development of software and data structures. VLBI data calibration. The plan is that NGHD will deliver calibrated, so phase calibrated and amplitude calibrated visibilities to the science teams. The main reason for that is that if you do that, you can average down the data and which is manageable. But we have to investigate what's necessary to do that at the scale of the NGHD. There also may be additional requirements. So one of the things I learned here is that the prototype receiver is likely to be only deliver linear polarization. So we'll have to do a similar trick to what's already been done in the UAC for ALMA, where the linear polarizations are converted into circular polarization. For a single dish, that process software exists to do that, but there, for example, it may very well be very useful to have phase scale calibration terms inserted into the signal, because that can help with the polarization, the polarization conversion. And then we are thinking about a memo about basically how do we organize the compute infrastructure. One of the issues we're facing in EHD is that there's several platforms that people can use, but there's no central identity management authorization. People share passwords. That's not the ideal way, especially if there's many more people involved with the project and you want to control who has access to what data, and people can actually find the data. A guiding principle here that's in many parts of science is surfacing are the FAIR principles. Make your data findable, accessible, interoperable, and usable. And that has consequences for what kind of data formats do you use, but also how do you have a search engine in front of that people can actually find the data. A little bit more details on the recording. The data rates are significantly larger than HT. If you actually calculate the data rate that's coming off the full phase 2 NGHD is a significant fraction from what the GEANT network, which is the the international network that connects all the different European countries provides, with the backbone of the internet, the research internet in Europe. So obviously that's not going to happen. There's no way our project can consume, say, half of that bandwidth. So the current thinking is that we'll still have to ship recorded media to most stations. But e-transfer, electronically transferring data from the stations, might still be desirable to run, for example, fringe tests, where at the start of an observation, you quickly transfer a little bit of data to the correlator, run the correlator almost in real time, such that you can give immediate feedback to the stations and check whether the system is actually working. Because there's no worse thing than doing the observations and finding out 6 months later that because of an error at the telescope, the data is useless. There's also interesting trends on the recording media. SSDs are expected to actually are cheaper by 2030 than hard disks. The total volume of SSDs, I think, is already comparable to traditional hard disks. So a lot more development is going there. Some people even think that the hard disk technology will not evolve much further because it's there's no money to be made there anymore. And then we have to think about shipping disk modules versus maybe complete units. Right now, you have Mark 6s in the EHD, which have modules with 8 hard disks in them that you can take out, put in a box, and transfer. The problem is, on the other end, you need a similar machine to plug in that module to do the playback. Whereas if you look at how the industry ships large volumes of data, for example, to cloud infrastructure, they actually do this by shipping effectively computers with the disks in it that have a fast network connection on the end. And what they do, they plug in the power, you plug it into the network, and then they transfer that data. The extreme example is Google and Amazon. I believe both have a solution like that, where someone drives a truck to your place and transfers it, loads the data to the truck, drives it to the data center, plugs in the truck to the data center, and transfers the data. I'll skip this in view of the times because I want to talk about correlation as well. So we're looking into what correlation platforms are available. Currently, we correlate on dedicated clusters. We think that's still a good way, but maybe we should think about hosting that dedicated cluster somewhere close to where there's a lot of network bandwidth available. Another solution is generic HPC infrastructure. For example, the Australian long baseline array does all that correlation on a shared supercomputer in Perth. But that has consequences for how you do the data transfer. Another option is cloud, and there's within the GHD, there's a study being done about how effective and how quick you can correlate there, and also how cost effective it is. Something that's important development is there's quite a bit, several groups that are looking at GPU acceleration of the correlator. There's now a GPU version of the DiffX correlator that the EHD uses, and a fairly new development is that GPUs now have different compute units on them called tensor cores that are very suitable for at least the correlation part of the correlation, what we call the X part. Really is an order of magnitude faster. Although to benefit from that, the benefits are mostly in cases where there are large numbers of antennas. So for us, it's probably a little bit of a less improvement. But one of the insights is that you maybe can then use a less powerful GPU that is cheaper and doesn't consume all the power. And another thing to think about is this is important for, I think, for the backend design, is that channelization is important. If you subdivide the total bandwidth of that come from the receiver in smaller subbands, it becomes easier for the correlator to parallelize. So in the first example, there's 4 bands and all the stations do the channelization in the same way. So basically you can have 4 correlators in this example running in parallel, process each a fourth of the total bandwidth. Important there is also that there's actually, if you look at the spectral channels that come out of the correlator, there is actually an optimal number for CPU correlators that's in the order of 500 channels. For GPUs, that's probably a little bit larger because they handle that sorts of FFTs better. If you go to the next example, there's some differences in the channelization, but it all still fits. And you can still have a factor of 2 parallelization there. It's not ideal, but we can probably handle it. At the right, very right, there is the current HT case, which is kind of a nightmare because the different channelization and also the different sample rate means that you can't really split this into multiple correlators. It needs to be a single correlator where all the data at some point comes together. The fact that the sample rates are different means that you have to have FFTs with very long length which are suboptimal. So in conclusion, data management is a significant challenge. Even the correlator is mostly a data management problem. It's also compute, but typically the bottlenecks are actually getting the data into the CPU, into the GPU as well. And there are significant dependencies on the operational model manager correlation platform. Questions?
Thank you, Mark. We have time for a few questions. Remo?
I fully agree.
Could you repeat that? I think the mic was off.
I thought so that the mic was off. Yeah, this is a lot better. So basically this is an ICD issue because Alma designed their correlator incorrectly after having been told to use 4 gigahertz by the VLBI people, and the VLBI people actually never realized that was going to be taken literally and not like 2 to the n, 4096. So let's fix that.
And I still agree with that.
Jonah?
Since there's a gap, Remo and Mark, great talk, Mark. I thought actually that VLBI was de-scoped from Alma's mission, just as it was from SMA's. And so I don't know the history that you relate, Remo, but it doesn't strike me as they made a mistake. They just didn't have something to consider. And you're shaking your head, so I would like to get the backstory from you. But they are indeed, there is indeed an ALMA 2030 correlator project presently right in progress. And actually the correlator project doesn't include the A to D converters. It's really the A to D converter project, which is being run out of Bordeaux, which ought to be influenced. And you know, the problem which arises is how do we get the message across? Because that is highly non-trivial, even though EHT is making a big splash and ALMA's participating and so forth. So I'll just note that.
I'd like to emphasize Jonathan's point. So Mark, in the people you have so far signed up for the data management group, is there someone from ALMA?
There is not.
What?
There is not.
Yeah, it might be useful as a group to reach out to ALMA, or to maybe even to invite someone from the ALMA correlator development, or someone just even to sit in occasionally, just to make sure that at an early stage they're aware of what's going on and what's to come.
A very good idea.
Thank Mark again. The next talk is by Sarah Issaoum on 86 GHz.
Okay. All right. Hello, everyone. So I'll be talking about adding 86 gigahertz to the frequency setup for the NGHT. I work on this project mostly co-leading it with Dom Pesci and Mike Lulov, who I wanted to highlight. We also had a lot of contributions in this case study by Andrew Shale, student Romy Aaron, of course, Maria Rioja and Richard Dodson, Alex Raymond, and others. So the key questions to explore as part of this case study was how do 86 gigahertz observations with the NGHT actually enhance the science capabilities we want to do at 230 and 345 gigahertz? What are the capabilities of standalone NGHT observations at 86 gigahertz, for example, on its own, or with existing or upcoming facilities like the GMBA or the NGVLA? And how can NGHT at 86 gigahertz be utilized as a community instrument in terms of time allocated for the NGHT telescope? So for this case study, we used the reference array configuration where we have this NGHT-A and the NGHT-B possible stations. They have different dish sizes and different site locations. And the EHT array is the same in both cases. We looked at possible combinations of just the NGHT new sites on their own or in combination with the core EHT sites. So here we actually show the fractional changes in UV coverage over the course of a year for the different EHT sites. So the EHT is in, and then we have various combinations of either the A array, B array alone, or in combination with the sites for different frequencies. So 86 gigahertz here, 230 up here, and 345 gigahertz up here. And then you will see that at 86 gigahertz, the conditions are extremely stable for the entire year, much more than they are at 230 or at 345. So actually for the entire year, 86 gigahertz observations could fill out the telescope time when the weather is too poor at the higher frequency observations. So 86 gigahertz capabilities would also enable NGHT to interface with other facilities like NGVLA and GMBA when it cannot observe at 230 or 345 gigahertz, when the weather conditions are not optimal for these observations. This actually gives a huge amount of time during the year where NGHT sites on their own could carry out science at 86 gigahertz, either alone or with other facilities. So we also looked at the zenith opacity cutoff for different sites. So we're looking at the number of sites available that have a zenith opacity below 0.5, where we would accept this limit to be kind of acceptable observing conditions at different frequencies. And here you can see that for 86 gigahertz, it's completely flat, whereas for other frequencies, we can have certain site drop-offs at different parts. You'll notice a lot of the site drop-offs happen in the summer because quite a lot of the sites are in the northern hemisphere. So this is where the weather degrades. Yeah, so 86 gigahertz is incredibly stable, which actually guarantees full coverage with the entire array at any time of the year at 86 gigahertz. So an interesting aspect we want to show is multi-frequency imaging. So one of the major goals of the NGHT is to connect the black hole shadow to jet and outflow physics, especially looking at spectral index, rotation measure maps across 230 and 345 gigahertz. So we're thinking about how does 86 gigahertz actually help us here? Of course, it adds multi-frequency information by looking at spectral index over 3 frequencies instead of just 2. That is obviously very informative when we're looking at larger scale jet emission at 86 gigahertz. But also, multi-frequency imaging is an incredible tool combined with 86 gigahertz capabilities to enable NGHT sites on their own to do reconstructions of the black hole shadow and the jet. So here we have reconstructions without multi-frequency imaging. On this slide, you will see at 230 gigahertz, the NGHT sites on their own without the EHT array. And here's what they're capable with the EHT array. So you'll notice the nice shadow and the jet structure for this, this image. Now, if we add multi-frequency capability, we add 86 gigahertz. This is what happens. So with 86 gigahertz, the NGHT sites alone, without the EHT, are able to get the black hole shadow and the jet if we add 86 gigahertz information and we make use of multi-frequency imaging tools. This actually means that for the majority of the time when you can observe at 86 and 230 gigahertz, you can do long-term monitoring of M87 just with the outer NGHT sites on their own. Which also alleviates pressure from the EHT sites to participate given they have their own observing programs. And then if we add 345 gigahertz, so we have 3 frequencies altogether, you'll notice that in both cases, both for NGHT alone or the full array, you get much sharper shadow and you get a very nice high fidelity image of the large scale jet. So this particular boost here from 230 on its own to adding 86 gigahertz, I think is incredibly compelling for the case of adding 86 gigahertz for core NGHT science. Another amazing aspect that we can make use of is this frequency phase transfer. This is work mostly led by Maria Rioja and Richard Dodson. If you were at their breakout session yesterday, you heard all about this. But with simultaneous observations, phase solutions from 86 gigahertz can actually be used to correct for this tropospheric phase errors at 230 and 345 gigahertz. This significantly extends the time of the year and weather conditions where we can observe at high frequency. It can actually improve the coherence time at the higher frequencies from seconds to minutes. But it's really, really recommended to have frequency bands of integer multiples because phase ambiguity actually causes coherence loss. So it's better to have integer multiples. So we looked at what will be the proper frequency setup. And we have this figure here that actually shows the frequency bands that would be preferable at 230 and 345 to overlap with the 86 band. That is, I think, 82 to 86. So it would be around in the 250 range, 250 to 260 in the 230 gigahertz range. And then 345 actually fits nicely as an integer ratio with 86 gigahertz. The only slight issue would be the 230 band would actually be shifted up to have the integer ratio. But for this method to work at this high frequency, simultaneous observing is absolutely necessary. So Maria led some work where they looked at frequency switching with the VLBA between 43 and 86 gigahertz, which didn't work as well as the simultaneous frequency phase transfer that they did with the KVN, which worked amazingly smoothly, even at higher frequency. And so it is incredibly crucial that 86 gigahertz be simultaneous with the frequency at which we need to transfer the phase. So for NGHT science, multi-frequency imaging helps us really connect the black hole shadow to jet outflow physics. And we can do this without the EHT sites for most of the time. We can do spectral index, rotation measure maps across frequencies. We can do time lags, core shift, and flaring behavior studies with simultaneous observing. We can do phase referencing and astrometry because 86 gigahertz can anchor the NGHT sites to a well-exercised astrometric network at lower frequency instruments. But phase referencing requires simultaneity again. Observing at 86 can also offer telescope calibration advantages where we can point and focus at 86 gigahertz when the weather is marginal at 230 gigahertz and improve telescope calibration. We could do long-term monitoring of near horizon and jet sources at 86 gigahertz that would enhance NGHT science. And we can look at transients because transient observing requires observing flexibility, and at 86 gigahertz, the entire year is available for transient science. And as a standalone array, we want to compare to what's existing or upcoming. This is a coverage of the GMVA array. This is the NGVLA. So if we look at the two, the GMVA has a long baseline range coverage, and NGVLA has very short range coverage, but very high sensitivity. This is what the NGHT looks like compared to the two arrays. I can flick back and forth. You'll see it is actually pretty comparable to the GMVA, but with slightly higher resolution. It has longer baselines, and it has much higher sensitivity because currently the GMVA's recording bandwidth is 4 gigabits per second, which is limited by the VLBA recording bandwidth. And with the NGHT, we're going to go to 256 gigabits per second, which is an incredible increase in resolution in bandwidth, which will also enhance polarimetric science at 86 gigahertz. So the entire observing year is available for 86 gigahertz science when 230, 345 is not possible. So we can actually observe with NGHT alone, or we can combine it with other facilities. So NGHT has excellent angular resolution, but relatively poor sensitivity because we have these small dishes on their own. So we're looking here at only the outer dishes, not the EHT array. NGVLA has excellent sensitivity, but relatively poor angular resolution because it is mostly in the American continent. If we put them together, you actually get the best of both worlds. You get high resolution by the NGHT, and you get high sensitivity and dynamic range with the NGVLA. So we're looking at simulations of M87 at 86 gigahertz and see what the NGHT could actually bring to NGVLA imaging. So here's what the NGVLA would see of M87 at this frequency. This is in log scale and linear scale. So we don't see the shadow, but we get the jet structure pretty well with the NGVLA alone because it has really good dynamic range and sensitivity. This is what the NGHT plus EHT would see alone without NGVLA. So it would see the shadow and would see some of the jet. But thanks to the combination of the NGHT plus NGVLA, this is what we would see. We would see a much sharper shadow thanks to the convergence advantages of having the NGHT and the NGVLA. So NGVLA gives information about large scale jet, which helps convergence of the jet structure much faster. And then the NGHT would drive the imaging of the central shadow. And so we get much better images of the black hole jet and the shadow at 86 gigahertz. This is what we would see if we have a fairly optically thin accretion flow for M87 at 86 gigahertz. So even 86 gigahertz alone, if this is what M87 looks like, we would be able to monitor this connection of the black hole shadow and jet the entire year with these two arrays. So we luckily finally yesterday finished writing this 86 gigahertz memo that encompasses all the work we've done as part of this project. We've been working on it for a few months now. The primary output was this memo. We began this project in October. We did a first draft yesterday that actually was sent around to our collaborators today. We have a read-only link to the current draft that can be found here. If you're interested, everything I've presented today is in this memo in more detail. And if you want to give us feedback, you can email Sarah, me, Dom, or Freek. And I also want to mention that we are organizing an NGHT workshop in August called Broadening Horizons, Exploring Multiband Capabilities for the NGHT. It will be held at Harvard on August 22 to 26. The workshop is centered around actually discussing the concrete impact of 86 gigahertz capabilities on instrument design and key science goals of the NGHT. The goal is to really determine the frequency setup of the NGHT, where we want to consider receiver build, multi-frequency phase transfer, and interoperability with other arrays. We have lots of different people coming with different backgrounds and expertise to actually nail this down. We anticipate this workshop to be a major step forward in the design of the next generation EHT instrument. Attendance is by invitation, but we have slots left. So if you're interested in contributing to discussions, please get in touch with me and Dom, who are the lead organizers of this workshop. So I'll leave my summary up, but if you have more ideas for 86 gigahertz utilization, I know we didn't talk about Spectraline, which is another big one because 86 has these amazing SIO masers, lots of interesting science that could be done with 86 gigahertz alone. Please get in touch. Thank you.
Thank you, Sarah. Avery?
So phase transfer seems like black magic. One, how credible is it that you think we can get phase transfer through 45? And then two, why is it impossible to get to 690?
Yeah, so we actually asked this question to Maria yesterday. I can also let her speak, but I can tell you what she said yesterday is that from their test of the KVN, there seems to be no upper limit at how far you can phase transfer. So you could do 690 if you want, but I'm sure there are other considerations to observing at 690 that would make things tricky. But essentially, yeah, the phase transfer is possible and has given already great results for the KVN at slightly lower frequencies. I think eventually we do want to test them at NGHT frequencies to make sure that it works. But according to their simulations, which fit really well with the observations of the KVN, everything seems to be working fine. I don't know if Maria, you want to add something. Oh yeah, it requires source detection at 86 gigahertz. That's the only caveat, which is tricky for Sagittarius A star because of the scattering at 86 gigahertz. But Richard actually gave a really good case yesterday that shows that if we do this clustering of kind of subarrays at 86 gigahertz for Sag A star, it could also be done.
Your errors of the low frequency are scaled up. Okay, so your errors at the low frequency are scaled up. So there, in that sense, there's an upper limit. There are penalties.
And the transmission at 690 is, of course, significantly lower. So you may not even see the source. Yeah, if you're at the low side.
Okay, Michael?
I've been following this for a long time, but seeing it all in one place, it just seems so obvious. I mean, amazing job selling it. Like, let's do it. And I sort of feel like Avery, we should make sure our design doesn't freeze out higher frequencies if we find that maybe 345 really works. I was curious on the NGVLA simulations that you were showing. Is that the entire NGVLA or just the extended sites that they're using for VLBI?
This is a question for Dom, I think, but I think it uses the central one as a single station, and then they extend it. I don't know where Dom is. Is that right?
Yeah, I'm up here. It does assume that there's the compact core component of the NGVLA would be sort of phased up as a single dish or as a single station. But then the outrigger sites are just sort of also assumed to be single stations here. They may be multiple stations at the actual final NGVLA design.
So how much do you think that depends on that core? Because maybe we could get
the sensitivity is definitely dominated by the core.
Yeah.
Okay. Yeah. Okay, great. Thanks.
So I have a quick clarification question. by small dish at 86 gigahertz, you meant 6 meters diameter?
Yeah, so we tested both cases, A and B. I think A was the 6 meter and B is the 10 meter. Or the other way around.
Okay, any more questions for Sarah? Okay, let's thank Sarah again. And next talk is by Gopal Narayanan on the dual band receiver.
Hello, everyone. So today I'm going to talk about the dual band receiver prototype that we're putting together at UMass. Thank you. So the outline of my talk is going to be as follows. I'm going to describe the 1 millimeter current band status of the 1 millimeter band, and then talk a little bit about the LO system that's being used, and then try to point out how we are going to do focus and pointing measurements for all these smaller dishes. If this could be the prototype with a beam switching system in place. And then I'll spend a little bit of time on the 850 micron prototype and what's being done about that. And I'll end with the status and timeline. Shown are some of the principles involved. On the UMass side, there's a lot of people in my lab that works on this, including Sandra Bustamante, who's a grad student there. That's my grad student, works on this receiver. The JPL subcontract has Jacob Cui leading most of the technical work, including Bruce Bumble, that does a lot of the SIS superconducting mixer fabrication. And SAO, Shep, works with us on the JPL subcontract. So the motivation, I think this is selling to already the converted for a dual frequency receiver. You heard in yesterday's breakout session by where Maria and Richard talked about this FPT technique, why dual frequencies could be good, or multi-frequency synthesis is very good. And as an example, I show a simulation done by Lindy here, where you take a truth image and you just use the EHT array. You are not really getting the extended structure, but you include the NGHT and include the 345 gigahertz as well. Suddenly, you've not only gotten a much more sharper image of the array of the event horizon, but also the extended jet. So the other aspect of why we started out with the LMT as the place to put this dual frequency prototype is that with its large aperture and central location, it could serve as a valuable anchor station. And proving it at the LMT would then show the pathway forward for the other arrays. Oh, so this is the slightly older one, which had the weird aspects of the highlighting. But regardless, let's press on. This is a block diagram view of what the receiver looks like. It uses 2 orthomode transducers and the frequency diplexer. Shown on the top is the 1 millimeter complement of this receiver, and shown in the bottom is the 850 micron complement. It's simultaneous dual beam, a single beam, but dual polarization in each band. And the point that I was trying to emphasize is that we're trying to go for 5 to 6 times the quantum limit that you can reach. And that translates into roughly about 70 Kelvin single sideband at 1 millimeter band and 80 Kelvin in the 850 micron band. And they will feature LO systems shown on the right-hand side, which are fully phase locked and tunable, so readily change to any frequency you want, and fully remotely controlled and use the beam chopper for pointing and focus. So the secret sauce in doing multi-frequency band is the frequency dichroids. And this is now, by now, when we started out thinking about the project, it was still a uncertainty around this was high, but by now our Korean colleagues have really nailed this down. So it's used by the Korean VLBI network. These kind of dichroids, and shown on the right is a low pass filter dichroid idea, where you have a low pass filter and then a single mirror, flat mirror that diverts the beams. They do have some insertion loss. It's about 5 to 10%, but that can be mitigated by cooling it And you can also trade off this insertion loss by selection of appropriate bandwidths. So you can play some games there. And the nice thing about these dichroids is it passes both polarizations with minimal, with an angle of incident constraint that's easy to accommodate for a receiver builder. We've ordered a low pass filter from the QMC instruments, and we're going to be testing this soon this summer. So this shows you a kind of a transmission line plot for these kind of filters. So this is an example filter. This is what's predicted. And you can see that insertion loss I talked about at about the 5% level. The way we designed this receiver, and this when we started out this project, we decided since this is going to be the prototype for a lot of NGHT antennas, we tried to do everything in a very integrated fashion. And so what I'm showing as a block diagram here is how you do a dual polarization, dual sideband receiver, but we're putting it all together into a single metal block. And the reason for this level of integration, there are several reasons for that. One is that it makes it very compact and suitable for small telescopes. The other reason is that it makes the assembly easier and reproducible, and integration also with electromagnets being removed. If we use static magnets, as I'll display. So a lot of these details are thinking about using this as a prototype for rapid development for the future. So it uses a orthomode transducer and a square corrugated feed horn. And each polarization, if you look at it individually, uses a RF 90-degree hybrid and 2 superconducting SIS mixers, which are fed with a LO, which are 0 degrees. There is a superconducting 90-degree RF hybrid, and if you do the vector map in your head, you can convince yourself that these two together produces the upper sideband and lower sideband separation. And this applies to both polarization. So we went ahead and designed this using various electromagnetic simulators, and it took a while, but we could finally come up with a design that was very compact and pretty much shows you the same thing that I showed there. Square horn, OMT, 1 polarization, that is the RF 90-degree hybrid and waveguide, and those are the LO injections, and the SIS receiver sit there. So from concept to actual implementation, this is now a fully fabricated mixer block in our lab and shows you all the details. This shows 1/2 of a split block where you actually see 4 SIS receivers mounted in these locations. And shown here are the 3 magnets we use. So these are rare earth static magnets. For those that may know about superconducting mixers, they usually feature big, bulky electromagnets to suppress the Cooper pair tunneling, which tends to be a noisy process you want to try to suppress. And this is now done with static magnets through electromagnetic simulations. And we've succeeded in doing that, and so that makes it easier to make it more compact. And this shows all the other details. I'll just step through some of the assembly of this receiver. So you can now see more features of the actual waveguides. This shows the LO waveguide. It's not very clear in this photo, but there are actually 4 SIS junctions sitting in these channels. And shown here to the right are features of the IF circuit with an absorber to reduce cross-coupling between the two. And then this shows the NRAO, that this is the Alma design IF 90-degree hybrid that we have procured and installed. There's a lot of bonding, wire bonding that's in there, but all that is in place in this photo. And then we had to feature, for the compact nature of this receiver, this mixer block, we had to take GPPO connectors. These are very special type of SMA type connectors, which had to be modified to be soldered in. They had to be rounded off at various places so it would fit in. And then we, of course, there are all these absorbers to absorb the remnants of the LO, or the remnants of the RF and the RF 90-degree hybrid, and those are shown here. And these have to be carefully machined, but once you machine it, you can machine it in bulk, and you can easily insert it into these correct places. And that's done in these 3 photographs. And then in the test door, we are doing these tests for these 1 millimeter blocks. And that shown there is the actual mixer block is shown in aluminum in the top right there. And the IF LNAs, if you actually count, if you could count the cracks, you'll see there are actually 4 low noise amplifiers. Very compact, and for somebody like me that's been doing this for a while, this is such a dream to have such compact. These are commercial LNAs that are available. You can stick that in. And shown here is the LO waveguide that goes in and goes into a directional coupler at the bottom of the mixer block, and this is all held together and brought down to 4 degrees Kelvin in the cold dewar. So the LO that I just showed how that's injected, but the whole system is based on taking a Yig oscillator, which is an yttrium ion garnet type of oscillator system that's at low frequency, in this case 18 to 23 gigahertz. For the centimeter people, they probably laugh when I call that low frequency. But, and then, you know, that's just quadrupled, and then there's further amplifications and WBN amplifiers. And we have a nice space lock loop system that's built, custom built in a very small digital PLL board. And the whole thing has been locked, and it works well across the entire band. And with minimal AM noise, which is one of the problems when you take a LO system like this. And this is based on a heritage. We've already have such a system at the LMT that we built for the previous generation of EHD receivers. And the whole thing is under computer control as well. This shows the LO system in the test bench. It looks sort of ugly, but this is the test system, and this is going to be packaged up by the time it's shipped to the LMT. So we've measured the noise temperature, and the results are really fabulous. What I'm showing is a noise temperature measured at using the test dewar against LO frequency, and this goes from 220 here to 280 gigahertz. And to guide your eye, I also show 2 traces of what you would get if you have 4 times the quantum noise and for 5 times the quantum noise. Remember, I talked about doing 5 to 6 times, and you can see that this receiver already seems to deliver better than the specifications we set out to do. And this is exciting. It shows some pretty good performance for all the 4 pixels in this receiver. And then we've also measured, and this is somewhat preliminary data, but the sidebands at each LO frequency, and the specification of sideband rejection is about 10 to 15 dB. And our measurement setup suffers some issues in this particular measurement done in March, but these are meant to be lower limits to the sideband separation, and so we feel confident that we can hit that limit, the specification that we need. Now I'll just take a brief foray into how we are planning to do our focus and pointing measurements. And this is a sort of an important point when we are talking about moderate sized dishes like 6 meter, 10 meter antennas for the NGHD, where you need to be able to point. Perhaps the discussion could be very different when you're also throwing in an 86 gigahertz system for which pointing can be perhaps easier. But if you have to point at 230 or 345 natively, you want a beam chopper in front of the receiver. This shows what we call the MSIP receiver, the current receiver of the LMT with the beam chopper in front. And the way it works is basically it's a servo motor that's completely computer controlled and spins at a high rate in front of the receiver and chops and sends 2 beams on the sky, one on the source, one on the reference position in the sky. And you can basically do all of this synchronous detection in software these days. And so that's what's done. And we've demonstrated that this system is able to detect 1 to 2 Jansky sources readily. And with the 6 meter antenna, that this needs to be improved. And that's another piece of work that continues to need to be done. So, and now I'm going to switch over to the 850 micron band. So when we started, we needed to identify a source of SIS junctions. There were not a whole lot of options at that point that we had. So we entered a contract with JPL, and that's turned out to be very fruitful thus far. So the idea is that our JPL colleagues will produce the SIS junctions, and UMass would work with them in testing and characterizing these devices. And then we would build a very much a scaled model of what I showed for the 1 millimeter block. And so we would build a 345 gigahertz system, very similar, but use the SIS junctions from JPL. And JPL's been doing this with the frame concept, which I'll outline in the next few slides. It's rather elegant. It's a single frame can hold an 8 by 8 millimeter square frame, can hold multiple SIS devices. And the devices are built in this fashion. with nice little hammerhead type arrangements that allow alignment and installation into the block to be of great ease. And so they've already started building their blocks to test the SIS junction and the various circuitry to associated to bias the junctions. So work is proceeding well. And they've by now already started to install make the first sample wafer. And they have 7 test SIS junctions in there. And they've already done some cold IV tests, and that looks, current voltage looks very good. And so that looks good thus far. So in the remaining time, I want to just talk about what is the status and timeline of this project. So the 1 millimeter module, this shows our the work breakdown structure for our whole MSRI project, but the 1 millimeter receiver module, if you see all the percentage complete, it looks pretty good. It's overall in good shape. And we hope to, by the end of this fall, have it fully tested and ready to be installed on the cryostat. The 850 micron is still a work in progress. There's still a lot of work to be done. This shows various things associated with the timeline. But I'll summarize that in here. So overall, highlighted are the key time steps that you can think about. There's a lot of details in here, but let me just draw your eye and attention to the 4 or 5 important dates. So by end of this year, we would have finished the 1 millimeter block, and also JPL would have delivered all the junctions to us. And by next fall, we would have finished testing the 345 gigahertz receiver component altogether. And we would then commission, if you follow the timeline of various steps involved, we would commission this receiver on the LMT in March. And then, of course, what that entails is that we would remove the existing 1 millimeter receiver that's already there at the LMT and send it over to OVRO. I don't know if you listened to Janice's talk the other day, and so that would then be commissioned in OVRO to commission OVRO as a new member of the EHD array. And that's it. Thank you. I look forward to your questions.
We have time for a couple of questions.
Yes, thanks for great development here. So we are hearing during these days, and especially also this morning, the advantage of including 86 gigahertz in this study. So is anybody in the collaboration considering a 3-band receiver that would actually include you?
Yes, yeah, indeed. So very good question. Thanks for that. I didn't delve into that enough in this particular presentation. When we started out our project, our focus was on doing a 230, 345 gigahertz dual frequency receiver that was optimized for a lot of the array. And then Sarah's work really, and Sarah's group's work is really very important step to understanding that there is a great need for even an 86 gigahertz component to be thrown in. As it turns out, I think with the way this receiver is built, this particular receiver, it features 2 superconducting sets of mixers. And so superconductors by necessity needs a 4 Kelvin fridge and a 4 Kelvin system. At 86 gigahertz, there are commercial W-band amplifiers that you can purchase now from Lunoi's factory in Sweden. And it's very readily packageable into a very small cryostat running at 20 Kelvin. And so the idea that we've been thinking about, that I've been floating and talking around with the collaboration people, there's no funding for that in this particular project, in the MSRI project that UMass is working on. But I don't see any technical impediments to building an adjacent cryostat, or in the future, a larger cryostat that would house that. And the 86 gigahertz is actually, to me, technically nothing about it is very complicated. It is all about the diplexers and how to incorporate all 3 bands and the trade-offs that would happen inevitably by inserting multiple elements that are transmissively lossy at a few places. So you have to figure out the trade-offs. There will be some loss of sensitivity, but I think ultimately the common good that you get from, I've been very much convinced. I sat in the breakout panel yesterday. I'm very much convinced that that is the way to go. To somebody else's question about going even to higher frequencies, I think that is, this gives us hope, the FBT technique gives us hope that you could step up and do this.
Yeah, just a little bit of warning, and maybe Richard and Maria can actually confirm this, that in order to get phase transfer, you need a very stable environment between the receivers. So you'll need to do something to control the thermal environment of both, say, the 86 and the 230, 345. You know, keep transmission lines, IF lines really short. Otherwise, you get twists between the receivers that are difficult to control.
Fair enough. Good point.
I had a couple of questions about the beam chopper, but we have run out of time. So we'll talk offline. So let's go on to the next talk, which will be given by three speakers, Ranjini Srinivasan, Manuel Fernandez, and Emilia Mamani, on the block-down converter and digital backend development.
Mamani.
Can people hear me? Okay. Okay, so my name is Ranjini Srinivasan, and today I'll be presenting the current status of the SAO VLBI digital backend, which is a little bit of a misnomer because it does include some analog signal processing. And part of the talk, which will be the firmware part of the talk, will be presented by our collaborators, two of our collaborators, Manuel Fernandez and Emilia Mamani, after I finish my section of the talk. So here goes. Okay, so the context, a very brief system block diagram, the very fast 16 gigasample A to D. I'm just going to present a couple of metrics, which will be of most interest to this audience, the BDC prototyping efforts, and I will finish my section of the talk with the case, or to make the motivation to develop an in-house custom integrated ADC FPGA board. And you'll see what I mean by this when you see the current setup that I have right now. And of course, the firmware part, they will present some aspects of the core functionality, some of the results that you can see, and what's next. And of course, what's next, the big thing on what's next is the channelization effort. So please keep in mind that a bulk of this was developed by Kerry Hayward, who was my predecessor. The firmware part of it was developed by Kerry Hayward. So I will show the team next. And I want to give a shout out to Ganesh Rajgopalan, who actually kickstarted the BDC design effort with John Test. And John Test is the IFLO engineer at SMA with whom I completed the block-down converter. And I'm not sure who that person is in the middle. So anyway, that is Kerry, of course. And this is the big group of collaborators I have. Oops, sorry. I jumped the gun there. And Ariel, who is the leader of this group. I want to give a shout out to Ariel, and he's a mentor for a lot of students in this group, including Manuel and Emilia. And let's proceed. Okay, so this is the architecture, and everything in this, oh, good Lord. Everything in this is in the red rectangle is basically within my purview of responsibility. Everything outside is some other subsystem. So this is the BDC plus DBE subsystem. You can see the BDC, two BDC blocks being fed by the 230 and 345 receiver. If you notice, the IF is 4 to 12 gigahertz. What comes out of the BDC is baseband DC to 8. And the so there are 8 BDC channels as total as of now in this development effort. And the baseband feeds or is digitized by 4 of the fast A to D converters that I was talking about. 4 of them, and they're on a single board, and they feed into a single FPGA. This is actually an evaluation board from Xilinx, and it houses a Vertex Plus ultra scale FPGA, which is actually quite a powerful FPGA. The output is a 100 gigabit interface, and you can see the QSFP28 connectors, which go through this 100 gigabit switch into the recorder and so on. And you can see the external parts of the other subsystems, the EHT monitor and control, the piping coherence, of course, everything, the LOs and the ADC clocks are all locked to the 10 megahertz in the maser. And you can see the 1 PPS feeding into the FPGA board. And of course, we have test equipment, local monitoring control, and all the monitoring control will eventually be done through the 1 gigabit interface. Okay, so I'm going to show you the test setup in my lab, and here you can see. I just want to point out that the 4-channel ADC board was designed by Rick Raffanti, who's an external contractor. And you can't see the 4 ADC boards, which are actually sitting below this big aluminum heat fin and this giant fan. You can see the clock source clocking the ADC board sampling, which is running at actually 16.384, slightly higher than 16. So, and right now for testing, of course, I have a tone source connected to one of the RF inputs feeding into one of the A to Ds. Actually, right now I have it being power split into all 4 inputs. And on the right here, you can see the VCU 128 evaluation board, again, with this gigantic heat fin and the QSFP connectors, which are part of the 100 gigabit interface. And as I said, this is right now a little bit incomplete because right now I have it connected to the 100 gigabit switch for testing purposes. And this, by the way, this was designed actually by Rick Raffanti even before I joined SAO last year. So there were some issues with the initial revisions. The final revisions were completed and he tested and verified this even before I got here. And then I want to just point out a couple of brief metrics for the A to Ds. And here you can see, just want to mention that on the left-hand side, I am plotting the signal to noise, but with a slight difference. This is the signal to noise and distortion, because obviously a real life A to D is not going to have the ideal signal to noise ratio, which for a 4-bit ADC is 24 dB. You can see for the 4 channels, it's somewhere between 20 and 20.5 and 21.5. The effective number of bits, which is probably of the most interest to most people here, is somewhere, it's not 4 bits, as you can see, it's somewhere in the region of 3.25 and slowly walks down with frequency. And this is about the end of the first microzone. So this is on the left axis, this is the right side axis. And this is good enough for, as you say, most work. It's not usable, of course, in the second microzone. So the next and only other ADC metric that I want to present is the noise power ratio. And I just finished this doing this measurement, which basically shows the optimal loading of the A to D. You want to load the A to D with optimal power. The black line, oops, oh, crap. I apparently can't keep my pointer in. Okay, so the black line is the ideal curve, NPR curve, and the peak of that NPR curve shows the optimal loading. And you can see the red dots are the actual measurements, the green is a fitted line, and you can see the fitted maxima are slightly different, of course, because this is not an ideal A to D. And what does ideal loading mean? It means that if you're on the left-hand side of this peak, you're underdriving the A to D, so you're not toggling enough bits. If you're on the other side, you're overdriving it and essentially clipping it and losing information. So you want to try to load the ADC as much as possible at the optimal loading factor. And keep in mind, of course, that if you notice here, I say that this has been done at a notch frequency. This has to be, of course, characterized across the bandpass. So I've done it a tunable filter, which is really nice with several frequencies, but really, really expensive. So we have 4 filters. I've done this at 7.025 gigahertz. I have repeated this at 6. And they look very similar. I have to do this at a couple more frequencies. Then I find a nice median to load the A to D with. So anyway, and I'm going to switch gears now and basically just go through the BDC highlights. The block down converter is the signal chain is of not real interest. I just wanted to pay attention to these 2 round things here, which enclose the 2 mixing stages, and these rectangles here, which enclose the filters. And what you can see here is that the receiver input comes in at 4 to 12. You have the block output coming out at DC to 8. And that leads me to the BDC highlights. Of course, as I mentioned before, the Nyquist bandwidth is 8.192. It has an up-down converter design because of those 2 mixers that I showed you to prevent leakage from input to output. And working with Gopal, I think the interface to the receiver has been more or less well determined. I'm using cascaded filters to get a very deep projection of the first LO and the unwanted image, of course. And I've set it up such that no stage will go into compression by at least a margin of 10 dB if I stick to the power requirements. And I'm implementing a servo for the input stage and an automatic gain control for the output stage so that the ADC is optimally loaded at all times, as I mentioned before. And I have additional monitor points for debugging purposes, both at the input and output stages, so that one can use a power meter or spectrum analyzer to look at the bandpass. And so far, I haven't added slope equalizers, but they can be added, and I have enough gain to cover the loss. Okay, so finally, this is what actually the prototype is going to be delivered. It has passed for preliminary design review. Ganesh was very kind to help with that. And X Microwave, which is a company which is actually going to be delivering the prototype, has these individual components in these PCB drop-in modules, which is stick on this prototype evaluation board. So they're going to test it and give it to me. And of course, I'm going to test it again and evaluate it with all the right transfer functions to make sure that this works as intended. If it does, then we send it out for a full-on fabrication. So these are, of course, the MMIC components. So, and then the very last thing I want to mention very briefly is the motivation to an in-house custom ADC FPGA board. You saw those two separate boards. Well, it's never a good idea. So the VCU 128 is an evaluation board. As they themselves point out, it's an evaluation board and not that suitable for deployment, especially deployment to remote sites. The other thing I really dislike about this board is the FMC connector that actually makes the two boards, which you didn't see in that because they're not visible. It's not a very reliable high-speed connector. You have to do a lot of mechanical rejiggering to make it reliable. And I'm actually having intermittent connectivity to 1 gigabit, which I believe Manuel has starting to resolve, which I'm very happy about. But still, I'm still a little not convinced that the evaluation board is the way to go. And the other thing that worries me is when we start using the DSP slices, which we're going to max out probably when we implement the channelization, I worry about performance. The pros, of course, of using the setup as is that the boards themselves, the evaluation boards are very expensive. The chips, which form the heart of the FPGA, are seriously expensive. So unless we can get them donated, and Beijing Jono, they might actually even be unavailable due to the supply chain issue. And of course, the nice thing about this is it's already designed. This two board solution is already there. It's a part of the system. So we may go with it, at least for the fringe test for now. So I'm going to stop here and hand it off to my collaborators to continue with the program. Thank you, Manuel.
Thank you, Ranjani. Hello, my name is Manuel Fernandez. I'm a student, and I'm collaborating with my colleagues from Argentina on the digital backend firmware development. Okay, so just to start, I would like to present you this block diagram right here, where we can see some key aspects of the design. And well, to start, we have the ADC board here, which consists of 4 ADCs running at a sampling frequency of 16 gigahertz each. And the data sampled by these ADCs is converted to 4 bits on each ADC and transmitted to the FPGA at a rate of 16 gigasamples per second. Now, on the other hand, we have the FPGA board, which is in charge of the reception, processing, packetization, and transmission of the data sampled by the ADCs. Now, we have three important points here. We have the start point there, where the data is being fed into the FPGA through the pipes. Then we have the endpoint there, where the data is being sent to the switch over the 100 gigabit interface. And then we have a bridge point here, which is a monitor and control block that will interface this whole block with a computer using the UART and the 1 gigabit interface without using any microprocessor in this case. Now, we also have 2 important paths. We have the pipe to FIFO path, which includes in the middle the processing state, which right now is the dark side of the development, but it will include the channelization, requantization, among other features. And then we have the FIFO to CMAC path that includes in the middle the packetization stage that will receive the process data from the processing block and will wrap it into the VDIF frames to send them over the 100 gigabit interface. Now, we also have a helper block here, which is a timing block that will produce timestamps for the packetization interface once it has found the GPS and locked it to the master provided by the ADC clocks that fit into the system. Now, I want to mention also that we have 3 clock domains here, 250, 322, and 50 megahertz. And we are, well, in this particular case, all of these blocks have been rewritten in System Verilog and validated by my colleagues and myself. Okay, moving on to some results. We have the alignment results in the pipeline. And well, we can see here, we were testing the system with the tone source. And well, we are not aligned yet, but we expect to be aligned. So we should get sine waves in this case because we have a tone source on the input. Now, since we are not aligned, this is basically garbage inside the FPGA. And once we get aligned, we get this sine wave in each channel. Now, I want you to pay attention to this. We only have 16 levels because we only have 4 bits ADCs. And well, this is the best sine wave that we can get with 4 bits. Now, I want you to pay attention also to these spikes that we have on each channel. These are due to nonlinear effects of the ADCs running at frequencies higher than 15 gigasamples per second. And well, this is what we get. Now, we also implemented requantization, and we have this graph here showing us the requantized version of the previous signals. And we can see here that from 16 levels that we have, we came down to 4 levels, or this could be from 4 bits down to 2 bits. And well, moving on, we have the resources area and complexity inside the FPGA. We can see in this graph here, the area inside the FPGA, and this blob, this highlighted region here, is are the resources used inside the device. Now we can see that the ADC board, the pipes, ADC pipes, the CMAC, and the processing block, green, pink, and blue, they are the main contributors to the resources inside the FPGA. This is for the pipes and the CMAC, this is because transceivers and transceivers logic. And for the processing block, this is due to the lookup tables for the requantization stages and the average power calculator that we have on each channel. Now, talking about the complexity, we can look at that table, and we can see that we are not using any DSP slides yet, which is great because we are going to need them once we implement the polyphase filter bank, which is going to require lots of them. And it will also need block RAM that we are using only 6% of it. So we have 94% remaining, which is great because, again, the polyphase filter will need them as well. Now, regarding the CMAC interface, we have run some tests, and we have found that there is no packet loss. This is really good, actually, because we don't like to drop packets. And well, now we are hoping to get a license by Xilinx that will enable us to build up the link between the FPGA and the switch so we can measure the data rate between the two. Okay, so I will let my colleague Emilia continue. Thank you.
Hello, my name is Emilia Mamani, and I'm going to talk about the things that we are going to develop next in the DBA. So first is the 1 gigabit Ethernet interface. This one is the one that Ranjani mentioned previously. We're having connection issues. This is one way that we have to communicate the FPGA with the PC. The other one, that is the only one that we are currently using, is WART, but it allows only single reads and writes. So we want to implement this in order to be able to get full state of health packages from the whole system. So in the last few weeks, we found that in the 2 pins that we can see in red in the slide, we have an intermittent signal. So we believe that this is due to software or hardware configurations in the physical layer. And we believe that, the physical layer involves speed and auto negotiation. So we believe that this is directly related to this connection issue. Next, we have the storage implementation. Currently, we haven't got any recorder working, so we are trying to provide an alternative to this one. The storage implementation is in another BCU 128 board, and we want to be able to receive the data packages from the CMAC through the 100 gigabit Ethernet interface, and we want to check if the data is correct and check if the packetizer as well is working correctly. Next, we have channelization. In this part, we are investigating how to implement it in the FPGA board. When implementing this type of filter, you have to be very careful with the amount of resources used from the FPGA. So we based on a paper, on a study made by Primiani, Weintraub, here present, and others, in order to get these estimations, that these are the others and multipliers estimations, which translate into DSP slices that are the ones of the FPGA board. So here we have formulas that help us take into account for 3 factors. One, the MUX factor, the number of channels, and the taps. and the way that they affect the amount of resources used in the FPGA. We believe that, as Manuel said, that the most of the DSP slices are going to be used for the filter. But to this baseline estimation, we also have to add a 30% margin for coding purposes, and the other DSPs that may be used in other processing stages. So we have to be very careful to not surpass the limit provided by the current FPGA that we're using. And lastly, we have the verification platform that we are currently developing, because the way that we have to interact with all of this, with the debugging stage, is through the terminal. And we believe that it's not very friendly. So we want to implement this one in order to have a better communication and something more visual. So thank you, that would be all. And we are open to questions. And we also want to invite you to the breakout session this afternoon, where we are going to develop a little bit more on some of these subjects. Thank you.
Okay, time for a couple of quick questions. Jonathan? Shep, sorry.
This is a pretty simple question. I may have missed it, but on the block diagram, you have an input somewhere from GPS, right? So are you going to be able to just on the fly compare GPS with the major signal on the ticks?
On the fly, I'm sorry, what did you, I'm not quite sure what you asked me.
You're going to have a running comparison of the GPS to the major.
Right. The one PPS from the GPS input, yeah, the ADC board has an input for the one PPS.
Okay, I didn't see it on there. I just wanted to check.
Oh, I'm sorry. It was there.
Okay, fine,
oh,
fine.
sorry. It was coming off from the right-hand side and went to the, yeah, if you can just go right to the block diagram first. Oh, yeah, this one shows, but even the system block diagram showed that.
I was looking for an external thing.
Right. Sorry. Yeah. So if you go to the top level, Manuel, can you go to the first one? The very first block diagram. There we go. The GPS PPS distribution. Yeah.
Jonathan was next.
I only wanted to quickly comment that this is an absolute tour de force of work.
Thank you.
Between the hardware and the firmware, and that I can understand that it may be outside of the boundary of the usual experience of some of the people in the room, and we're going to be digging into this in a conversational way, and I'm very glad
in the breakout session. So Jono is also going to be talking about the DBE working group requirements, and we're going to dig in a little bit more into this.
I'm very happy that Emilia mentioned it, and it is 4 to 5 in the Curie room.
Yes, thank you, Emilia. I completely forgot about that. I also want to give a shout out to the engineering busy week that Janice mentioned yesterday that we're holding at SAO, and we invite contributions. I believe it's mid-July, it's either the July 15th or July 23rd week, and we invite contributions for our conceptual design review. And the systems engineering team can be contacted for that if you want to participate. So please give us input, give us feedback, suggestions, comments, everything.
Okay, I think Remo has withdrawn his question. So
no, Remo, please. I would
I'd like to start the end on an upbeat note. I have concerns, but I'll save it for this afternoon.
I'm sorry, I completely did not hear you.
Okay, let's.
No.
Oh, well, yes.
Okay, well, if you insist. I mean, I don't know enough about the details of this whole system, but I'm actually quite concerned that with the modularity of it, you know, one lesson that I think that the DBC3 teaches us is that having a highly modular system and it makes it very simple to operate. right? I mean, they jump from DBC3 to DBC4. So I'm not convinced that this model. The other thing I'm quite concerned about that a lot of things get locked in the design quite early on, and you cannot treat tri-band receivers sort of as an add-on. It requires space also in this system, right, to accommodate the correlation and et cetera, et cetera. So, you know, it's great for a prototyping system, but there needs to be a significant systems engineering step that may significantly change the designs.
Right. When we started this design effort, I was not aware of the 86 gigahertz effort. So I continued with the prototyping effort when I joined. And only of recent have we been made, it's been becoming clear, as Gopal pointed out, that we will need the 86, that we will most likely include the 86. The other thing that I will mention that is of course personal concern to me is what happens to all this if the bandwidth requirement changes, because it's entirely possible. See, I'm bringing up concerns myself. If the bandwidth changes to 16 gigahertz, which I believe that the JPL receiver is planning on delivering. I'm not sure Gopal can answer that a little bit.
Excuse me, I think we are now getting too much into detail. We have already gone over time. So I would like to end the session, and let's thank all the speakers of this session.